Hello. We're going to basically use the solution for this differential equation that we found for the simple harmonic oscillator. And we're going to start with that and the initial conditions. And from that, I'm going to work out what the actual constants are in the solution. And then I will apply that to find the equation for the position as a function of time, the function of velocity as a function of time, and the acceleration as a function of time. And then I'm going to use it to determine a velocity at two specific locations. So I worked this in class, but things got a little dicey, so I thought I'd do it again now. So let me start off by sharing my screen so you can see the actual problem we're going to be working. So it says when a 10.0 kilogram mass is hanging from a relaxed spring, the spring stretches 4.00 centimeters. The spring and mass are then set up horizontally on a frictionless surface. The mass is pushed in 3.00 centimeters to x equals negative 0.0300 meters and given a push in the positive direction, resulting in a velocity of 0.500 meters per second. So that means v0 equals positive 0.500 meters per second. Write the equations for position, velocity, and acceleration as a function of time. What is the velocity of the mass when it reaches x equals 0.0100 meters and when it is at x equals negative 0.0100 meters. So I'm going to record the key data there. I've got a mass that's equal to 10.0 kilograms. I've got a stretch, which I'll call just x, of 0.0400 meters. I've got mass that's at an x0 equal to 3.00 centimeters, which is 0.0300 meters. And I've got a velocity v0 equal to positive 0.500 meters per second. And ultimately, I want to know v when x equals 0.0100 meters and x equals negative 0.0100 meters. So that's the important data. Now I'm going to go ahead and stop share. Of course, you can pause this at any time if you want to copy that problem down. I'll also make it available in my Google Docs or by email. You can get them from me. So I'm going to stop sharing the screen now, and I'm going to go to my document cam. So the differential equation that we've solved here is for a simple harmonic motion, and this is not damped or anything. This is just f equals negative kx combined with m d2x over dt squared. So maybe I'll get better in a second, far as the focus goes. So I'll say m is equal to, or excuse me, m times d2x over dt squared is equal to negative kx. And of course, the negative kx is suggesting that the force is always in the opposite direction of x. So that's why we put it in there, because it is a restorative force. If you play with this a little bit, you just divide through by m and then pull the other side over there, we end up getting d2x over dt squared plus k over m times x is equal to 0. And that's a linear homogeneous second order differential equation. It's pretty straightforward. It's one of the simplest ones to solve. You can solve it with linear combinations of e to the constant times x and e to the negative constant times x, or you can substitute a trig function, something like that. So what we do, what we did in my class, is we're actually saying x is equal to a cosine omega t plus phi. By putting the phi and the a there, it's the second order differential equation. That means we've got two integration constants, if you will. I've included them as phi, the phase angle shift, and a, the amplitude. Now, if you take the derivative of this, you can say dx over dt, which of course is v. That's going to be, derivative of cosine is of course negative sine. So I get negative omega a sine omega t plus phi, where the omega came out in front because I first took the derivative of the sine with respect to its argument, and then I took the derivative of the argument with respect to time, and that gave me the omega. The negative is just because the trig function is the way it is. The second derivative, d2x over dt squared, which is actually the acceleration, is taking the derivative of this. The derivative of sine is cosine, so the negative will stay, but I'm going to get another omega, so now it's negative omega squared a cosine omega t plus phi. Ran out of paper there, but I think you can see it's a cosine omega t plus phi. So that's pretty straightforward. My cat has moved my camera. Aggravating little cuss. All right, so we now have the acceleration, we have the velocity, and we have the position as a function of time. In fact, if you plug this in, you will see that you get a nice result. Omega is got to equal square root of k over m. Well, we know k is going to be given from f equals, and I'm just taking magnitudes here, so I drop the negative, kx. So x would equal f over k. I mean, excuse me, f over x. Ooh, that's a bad looking x. Anyways, f over x. Well, the force is not really 10 kilograms. It's 10 times 9.8. So we have to do 10.0 kilograms times 9.80 meters per second divided by 0.0300 meters. And that gives us a spring constant equal to 49.50. And that's in newtons per meter. So we have K is equal to 49.50 newtons per meter. Notice I'm keeping an extra sig fig. I only had 3 going in, so I'm keeping an extra one. I could underline it if I wanted. The newton meter should have been in there, but obviously I ran out of paper, so that's why I come over here and write it. Now that I have that, I can compute omega, which is equal to the square root of K over M, so that's 49.50 newtons per meter over M, which is 10.0 kilograms. And you see what happens here is the Newton is a kilogram meter per second squared. The meters canceling out here, so that's a kilogram per second squared, and then the kilograms factoring out here are canceling out here, so I got a per second squared in the denominator coming up to the top. I mean, per second squared is in the denominator. When you take the square root of that, you get 1 over seconds, which is the same thing as radians per second. So this figure turns out to be 35.18 radians per second. Remember, radians is given by the formula S equals R times theta, so a radian is really not a true unit. It's more of it's actually a pure number. So I've got now the key values, 2 of the key values that we needed. We didn't need K so much, but we had to have K to get omega. So we got now omega, we got A. Now we can use our initial conditions. Our initial conditions are V of 0 is equal to positive 0.500 meters per second, and X of 0 is equal to negative 0.0300 meters. So now we can plug those in. I'm going to say that 0.500 meters per second is equal to negative omega times A times the sine of phi. Okay. In other words, I left everything in terms of omega and A. You'll see why in a second. But it's times the sine of phi, because the t is 0. That's what V of 0 means. The t is 0. So the omega t term that was in our velocity became 0. So I'm just left with the sine of phi. Now the other condition, I'm doing this in a weird way, but I'm doing it in a weird way because I know where I want to go. 0.300 meters is going to give me, in this case, it's the position, so it's the actual A times cosine theta. Now, again, cosine of omega t plus phi, but t is 0, so it's just cosine of phi. Ooh, almost wrote the same thing twice. That's the cosine of phi. So if I divide this top equation by this bottom equation, I pretty easily get 0.5 divided by 3. 0.03, negative, of course. So the left-hand side becomes negative 16.6. I'm going to keep an extra digit again, 7. And that just becomes reciprocal seconds. So I'll say s to the negative 1 power. And this a and this a cancels out. So I'm left with negative omega times sine over cosine is tangent phi. So I can find that phi is equal to the tangent inverse of, these two negatives will cancel out. I'll do 16.67 seconds to the negative 1 over omega, which we found was 35.18 seconds to the negative 1 again. And from that, we end up finding that phi is, if we keep it in radian modes, that would be best. So I'm going to say phi is equal to 0.4424, if I remember correctly. Yes. Radians. Okay, so there's another key parameter we needed. Now that I have that, I can go back and figure out what A is, say by putting the phi in the first answer. Or actually, let's do it in the second answer, in the second setup problem. So I'll say negative 0.0300 meters is equal to A times the cosine of phi, which is 0.4424 radians. So you got to make sure your calculator is in the right mode. And that ultimately gives us A is equal to negative 0.03320 meters, again keeping an extra sig fig like I've been doing throughout. So now I've got all my parameters. I've got the two integration constants, phi and A, and I've got the K and the omega, which are just come from the setup of the problem. So I can now write what x of t is. So I can now write x of t as equals A, which is negative 0.03320 meters, times cosine of, now I'm going to write 35.18 radians per second times t plus 0.4424 radians. The y of t, the v of t is going to be, notice we got v of t is negative of what we had before, omega a. So those two negatives are going to actually cancel out, and I'm going to get basically negative I'm going to get negative of negative 0.03320 times 35.18, and that'll give me 0.03320 35.18, multiply those two, and I get 1.168 meters per second times the sine of the same 35.18 radians per second times t plus 0.4424 radians. I'll put that right there, not the other parentheses. And then finally, I'm going to say A of t is actually omega squared times A. So I just have to multiply this by another omega. So that gives me 41.09 meters per second times cosine of 35.18 radians per second times time plus 0.4424 radians. And that finishes that off. So now I have x of t, v of t, and a of t. So the position is a function of time, the velocity is a function of time, and the acceleration is a function of time. Now the final part of the question wanted me to find what is the velocity when x is equal to 0.01. So one way you can do that is you can set x of t equal to 0.01, solve for t, and then plug that back into the velocity. So that's what I'm going to do. So I set 0.0100 meters equal to negative 0.03320 meters times cosine of 35.18 radians per second times time plus 0.4424 radians. Now, with this, what I'm going to do is divide both sides by this number, the negative 0.003320, and then take the inverse cosine, and I'll end up getting the inverse cosine is equal to omega t plus phi. So ultimately, what I can find is just using this in an equation form, calling this a x sub 0 or x for a question, so I'll call it x sub q. If I just solve all this for t, what I'm going to see is when I take the inverse cosine, this is the inverse cosine of xq over a, and then that's going to be equal to omega t plus phi. So I'll subtract phi from both sides, so I'll get cosine inverse of x sub q, meaning x that you're asking about, over a, subtracting phi from that, and then I divide by omega, and that'll leave me with t sub q. In other words, that'll give me the time that actually occurs, that xq occurs. So when x is equal to xq, this is the time period. So if I put these numbers in, I'll get cosine inverse, again using radians, of negative 0.0100 over 0.03320. Notice I just stuck the negative anywhere. It didn't have to be in one particular spot. Minus 0.4424 radians, so I don't really have to write that unit, over 35.18 radians per second. And sure enough, it gives you units of seconds, and I get 0.04077 seconds. Now all I have to do is plug that in. So I want V of 0.04077 seconds. And that, of course, is equal to 1.168 meters per second times the sine of 35.18 radians per second times 0.04077 seconds plus 0.4424 radians. And that ultimately gives me a velocity that is equal to 1.114 meters per second. So that's how you find the velocity at a particular position in space. We can do the exact same thing, putting, instead of 0.01, put a negative 0.01 in which case the two negatives are going to cancel out, but I'll get the same thing with regards to these two numbers. So literally the only difference will be this will be a positive sign. When you do that, you find that t at negative 0.0100 meters actually equals 0.02338 seconds. And then you plug that into velocity like I did there, and I find that the velocity at 0.02338 seconds, I found that was actually equal to 1.114 again. Meters per second. So is that right? Well, it is. It should be. I haven't made any mistakes. I've worked over this problem a couple times. You can see all of it in its entirety right here, and plus I'll take a photo of this. But in order to convince you, let me share my screen real quick. And I'm going to share this screen right here. Okay, so we're going to use Desmos. And what I did was I actually plotted, this is actually y equal to negative the amplitude times the cosine of, you can see it's actually cosine. If I move the cursor over, you see it's omega t plus phi, right? So that's the actual red line, and you see the red line, there's a lot of lines on it right now. That's not the more important thing. The red line is the actual x as a function of t. And then what I did was I said, okay, well, when x is equal to, or when the x position, which is graphed vertically here, when the x position is positive 0.01, what's the time? Well, lo and behold, 0.01 gives you 0.408, which we calculated 0.4077. So that's amazing. Of course, you can also see there's another one over here and another one over here. There's, it's going to continue. And when x is equal to negative 0.01, you can see it's 0.0234, and we had calculated 0.02338. So that looks pretty darn good to me too. The other thing is I went ahead and put the velocity up here. Notice I've got the amplitude times the omega, so this is the velocity equation. You can still see that I have the omega t plus that. So this graph is a tall red graph that you see. So if I zoom out a little bit, you'll see there's another red graph, and you can see that they're out of phase with one another. So the peak does not occur at the same time as the velocity versus time curve does. I'll move this up a little bit. So this is the actual velocity versus time graph, and since I'm now plotting v on the vertical axis, the x-axis is again the time. So if I want to actually check that the time of 0.0477 and the time of 0.0238 gives us the actual velocities that we calculated, all I have to do is plot those. So that's why I plotted these two vertical lines. And it's just a matter of finding out where it crosses that bigger red curve. So if I go down here, there's my two vertical lines. And you can see the velocity crossed. There's the 0.0234 seconds, and that is the time that we thought, and that is the velocity that we got, 1.114. And if we look at the other one, which is right here, we got time is the 0.04077, but in this case, the velocity is 1.114 again. So exactly what we got within a decimal place. So we know we did it correctly. That's a pretty exhaustive view of how to do that problem. I hope that helps you. I'm going to go ahead and call it a day. Have a good one.